Are you happy to receive visitors? Our solar system sometimes receives visitors from deep parts of the universe, and one visitor that's coming back to make another appearance is Oumuamua. Why the return, and what does it mean for our solar system? Stay with us as we dig into Oumuamua suddenly coming back and heading toward the solar system. Is it an asteroid, a comet, or an alien spacecraft? Oumuamua, a mysterious asteroid up to 400 meters long that entered the solar system, has confused astronomers for years. And Oumuamua, as astronomers dubbed it, was similarly unusual in that it resembled an asteroid yet behaved like a comet. Gravitational interactions tend to drive off some of the minor leftovers, such as comets and asteroids, as planets form around stars. When it was discovered, Oumuamua was categorized as a comet. However, the lack of a big puffy coma that streams out behind as a tail, as comets ordinarily do when heated by the sun, caused astronomers to doubt themselves. Some scientists speculated that it was a rocky asteroid or maybe a new class of interstellar object. Others argued that Oumuamua is a planetesimal, or a fragment of rock that was ejected from its original system by gravitational forces. It may even be a zombie comet, or as one publication put it, a monstrous, extremely fluffy aggregate of loosely bound dust grains left behind by a comet that disintegrated as it approached the sun. But there is a special reason for us to be interested in comets, as they preserve a snapshot of what the solar system looked like when it was in the stage of evolution that protoplanetary disks are now. Studying them is a way to look back at what our solar system used to look like during its early formation stage. These interactions propel the space pebbles from their planetary systems into interstellar space, where they can journey for millions of years. Now, the prevailing scientific opinion is that Oumuamua is a comet, since it's moving slightly faster than expected if it were only powered by gravitational dragging from the sun. The most likely explanation is that the object, like a comet, is outgassing material, creating jets that propel it forward. According to observations, it is 10 times more reflective than our solar system's native comets, possibly because Oumuamua's outgassing has blown dust from its surface, revealing dazzling ice beneath. This jet-driven motion almost sounds like a spacecraft that arrived from another star, made a fast pass through our system, and then rocketed away. And this idea has piqued the interest of astronomers, and researchers at the Search for Extraterrestrial Intelligence (SETI) listen for any potential technological signals leaking from the object, not once but twice. However, both campaigns received no response. Avi Loeb of the Harvard-Smithsonian Center for Astrophysics, along with co-author Shmuel Bayali, published his own hypothesis that Oumuamua was a gossamer-thin light sail, a sort of propulsion using the sun's photons from an advanced technological civilization. His rationale was based on the fact that outgassing would have changed the visitor's rotation period, an impact that should have been obvious but was not. Loeb speculated that Oumuamua could be a defunct piece of space trash that fell in our system by accident, or it could be an exploring ship dispatched to investigate our region. Of course, few scientists have supported Loeb's statement, but he believes that eliminating the possibility of aliens out of hand excludes useful theories that should be part of a reasonable study. But how did Oumuamua end up in the solar system? The space object was first observed by the University of Hawaii's Pan-STARRS 1 telescope. The object, which had circled the sun and was about to leave our solar system, was given the name Oumuamua, which means a messenger from afar arriving first. Astronomers around the world used telescopes to observe the interstellar visitor for 4 months before it became too faint to see. Oumuamua, on the other hand, didn't fit neatly into the presented scenarios. The item resembled an asteroid, but asteroids and space objects move owing to gravity. Oumuamua was accelerating as it traveled, indicating that it needed more than simply gravity to move. The object appeared to be pushed, similar to how comets are pushed when they approach the sun, and the evaporation of their gas and dust by the sun's heat generates a propulsive effect. The force of the expelled material also slightly modifies the trajectory of the comets as they orbit the sun, distinguishing them from asteroids and planets. Oumuamua, on the other hand, didn't resemble a comet, nor did it have a tail or an envelope of gas and dust known as a coma, which all comets have. Oumuamua's arrival immediately provoked controversy among astronomers. and scientific interest in Oumuamua grew as models to explain its acceleration emerged, implying pretty unusual chemical properties of the object. Two scientists eventually teamed up and began collaborating on strategies to test acceleration ideas for the interstellar comet. They came up with a theory. Oumuamua was envisioned by the duo as a water-rich comet traveling across the interstellar medium, or space between stars. Radiation battered the reddish object over time, causing hydrogen to develop inside the comet. Prior studies from decades ago showed ice could be transformed into molecular hydrogen, implying that a comet's snowball-like structure may contain the hydrogen in bubbles within the ice. The heat of the sun would then cause the bubbles to expel the gas in the form of a fan-shaped spray. When the body is warmed, the water ice restructures to a more stable and compact form, and the trapped gas can escape. According to the duo, this could explain Oumuamua's behavior without resorting to exotic chemistry or physics. The little object was driven by hydrogen gas produced from the interstellar comet. Interestingly, the lack of a dusty coma around Oumuamua can also be explained by the same situation. That is because even if there is dust in the ice matrix, you are not sublimating the ice, you are simply rearranging the ice and allowing hydrogen to escape, so the dust won't even come out. And this is exactly what interstellar comets should do. And observatories such as the James Webb Space Telescope can assist astronomers in understanding more about the formation of comets in planetary systems other than our own, as well as the composition of these exocomets, according to Bergner. When the Vera C. Rubin Observatory in Chile opens in 2025, astronomers hope to discover a few interstellar comets like Oumuamua each year, allowing them to better understand the characteristics of comets from other planetary systems. The solar system's comets and asteroids have arguably taught us more about planet formation than what we've learned from the actual planets in the solar system. It is believed that interstellar comets can tell us more about extrasolar planets than the extrasolar planets we're trying to measure. For 10 years, the Rubin Observatory Legacy Survey of Space and Time, or LSST program, will survey the skies over the southern hemisphere. If we had had the LSST online prior to Oumuamua's passage through the inner solar system, we would have discovered it much earlier in its trajectory. Because the object was so close to Earth, we could have sent a space mission to intercept and rendezvous with it. But there is hope, because when we discover more interstellar objects in the future, we will be able to send a dedicated space expedition to the interstellar object. Some scientists, however, are still nursing the hope of studying Oumuamua up close, which is the only way to learn more about it. And there is something to get excited about here, as there is a hope of catching up with Oumuamua. In fact, there are numerous proposals for missions that could accomplish exactly that. Consider Project Lyra, a proposal by the Institute for Interstellar Studies, I4IS, that would use advanced propulsion technology to rendezvous with and study interstellar objects, ISOs. According to their most recent research, if their mission concept launched in 2028 and conducted a sophisticated Jupiter Oberth maneuver, JOM, it may catch up to Oumuamua in 26 years. The Initiative for Interstellar Studies, I4IS, launched Project Lyra less than 2 weeks after Oumuamua was discovered. The goal of this concept study was to see if a mission to Oumuamua was feasible with current or near-term technologies. Since then, the I4IS team has done studies on catching up with the ISO utilizing nuclear thermal propulsion, NTP, and a laser sailcraft, akin to Breakthrough Starshot, an interstellar mission proposal that aims to reach Alpha Centauri in 20 years. Most previously proposed techniques for reaching Oumuamua using near-term technologies, as they detail in their analysis, call for a solar Oberth maneuver, SOM. The Sundiver, a concept by Max Planck Institute for Astronomy MPIA researcher Corinne Baylor-Jones, is an excellent example. This approach depends on the sun's radiation pressure to achieve a very high velocity with a light sail. The Oberth effect works on the principle of applying your boost when you are moving the fastest relative to the body you are orbiting, which in the case of the Sundiver is the sun. The closer your orbit is to the sun, the faster you will be. However, to benefit from the Oberth effect, you need to be able to bear the heat, as you must go as close to the sun as possible. At the heart of the SOM and other Oberth maneuvers is a technique known as a gravity assist, which has been used to explore the solar system since the early 1970s. The gravitational force of 3 bodies is used in this technique: the spacecraft, a second body that provides the assist, usually a giant planet, and the center body around which the spacecraft's route is controlled. The Solar Oberth Maneuver SOM relies on 3 discrete changes in velocity, aka impulses, to depart the solar system. These are some examples. To increase the spacecraft's distance from the Sun at aphelion on Earth, at aphelion to slow down and approach the Sun, to obtain an extra boost at the closest point to the Sun, perihelion, when the spacecraft is traveling at its fastest. Theodor Edelbaum developed his 3-impulse situation in 1959, but the word SOM appears to have stuck. It is fuel efficient for producing high speeds from the solar system. This is exactly what is required to catch an ISO after it has passed perihelion and is rapidly receding from the Sun. As the Parker Solar Probe demonstrates, getting closer to the Sun needs a heat shield capable of withstanding high heat and radiation. Parker's shield is around 2.44 meters or 8 feet in diameter and weighs nearly 72.5 kilograms or 160 pounds. While the size and mass of a heat shield for Lyra would not be the same, it's a safe guess that a solar heat shield would add a significant amount of mass to the light sail. And given that Oumuamua is our closest piece of interstellar material, the scientific benefits of a rendezvous mission would be immense. By mid-century, mankind may receive its first peek of what goes on in distant star systems for the relatively inexpensive cost of a rendezvous expedition. More importantly, it would be an opportunity to finally answer the numerous questions raised by Oumuamua during its historic flyby of Earth years ago. Oumuamua, however, may not be unique in coming from outer solar space. In fact, another comet that just made a dramatic swing around the Sun may have had an interstellar origin. Since its discovery, astronomers have been baffled by the origins of Comet 96P Mach-Holtz. It's a 4-mile-wide sun-grazer object with a strange set of features that suggest it's a visitor from another star system. For example, the composition of 96P is particularly unusual, and its orbit is strongly inclined, making it pass closer to the Sun than practically any other comet. These characteristics, among others, suggest that 96P was rerouted into our solar system by an accidental collision with Jupiter after its intergalactic journey. In an ironic twist, the comet's encounters with Jupiter have disguised its origins and raised the possibility that its peculiarities are due to genesis in an unusual portion of our own solar system or as part of a nearby celestial body that split away. But for the time being, the comet is yielding stunning photographs of its closest lapse around the Sun, known as perihelions, of its 5-year orbit. The comet reached its most recent perihelion, passing nearly 3 times closer to the Sun than Mercury. The Solar and Heliospheric Observatory SOHO, a joint NASA-European Space Agency space project, has been tracking 96P's perihelion since its inception in 1995. Donald Mach-Holtz, an amateur astronomer from California, was the first to spot 96P with binoculars in 1986. Recent investigations have revealed that the object is very low in common components such as carbon and cyanogen and does not appear to have the dusty atmosphere or coma present around other comets in the solar system. According to research and based on observations of 96P's perihelion, these traits suggest the comet may be a completely stripped-down nucleus with a primordial and possibly interstellar origin. However, even if we launched an intercept mission to the comet, we might be unable to answer tantalizing questions about the comet's past. But regardless of whether we learn more about the origins of this enigmatic comet, scientists are likely to discover many more interstellar objects in the coming years, following the discovery of the first confirmed interstellar comet, 2I Borisov, and the first known meteors that are likely to have traveled from another star system before impacting Earth. However, the intriguing similarities between the nucleus of 96P and Oumuamua may strengthen the argument for 96P having an interstellar origin, which means that its surface properties were acquired during millions of years of cosmic ray bombardment between systems, rather than due to evolution in our solar system. However, the riddle of 96P's genesis may never be answered, in part because it's a difficult item to investigate. Its tilted orbit never brings it very close to Earth, and its lack of activity makes it difficult to observe except near perihelion. Though satellite telescopes like SOHO may investigate it, many of the comet's mysteries, including its genesis, remain unknown. Now, on August 30th, 2019, Gennady Borisov, a Crimean amateur astronomer, found 2I Borisov. At his observatory, he was using a handmade telescope when he saw a faint object moving against the background stars. He reported his discovery to the Minor Planet Center, which confirmed the comet's identity and assigned it the provisional designation C2019 Q4 Borisov. Additional observations indicated that the comet had a hyperbolic orbit, indicating that it was not tied to the Sun and originated outside our solar system. Its eccentricity, or how far its orbit deviates from a circle, was 3.36, which was significantly higher than that of any known solar system comet, and it had a 44-degree inclination, which is the angle between its orbital plane and ecliptic plane. The comet reached its closest approach to the Sun, perihelion, on December 8, 2019 at a distance of about 2 astronomical units AU, or 300 million kilometers. It passed closest to Earth on December 28, 2019 at a distance of about 1.8 AU, or 270 million kilometers. It is now receding from the Sun and will leave our solar system for good. Now, 2I Borisov had a coma, that is, a hazy envelope of gas and dust surrounding the nucleus, and a tail, a stream of material driven away by the solar wind and radiation pressure. Its nucleus was believed to be roughly 1 kilometer in diameter, similar to that of many comets in the solar system. Its brightness peaked in late November 2019 at roughly magnitude 15, making it viewable only with big telescopes. Spectroscopic examinations found that the comet's surface was somewhat reddish, indicating the existence of organic compounds. Water, carbon monoxide, cyanide, and other common cometary volatiles were also detected. However, several differences were discovered, such as the fact that the comet had more carbon monoxide than typical solar system comets, indicating that it formed in an extremely cold environment. 2I Borisov is a once-in-a-lifetime opportunity to investigate an object that originated in another star system and has information about its development and history. Astronomers can learn more about the diversity and history of planetary systems in our galaxy by comparing them to solar system comets. The comet also sheds light on the origins of Oumuamua, the first interstellar visitor discovered in 2017, which resembled an asteroid in look and behavior. 2I Borisov will subsequently fade out of eyesight when it returns to interstellar space. We are unlikely to see it again unless we develop advanced tools to chase or intercept it. However, if new surveys and sensors increase our ability to detect intergalactic visitors, it is feasible that more will be discovered in the future.